session. So first of all, if there are any doubts pending in work by energy, we will clear that today. And then we'll be moving on to the next topic of heat and thermodynamics. So please let me know if you have any doubts in work by energy. Any questions from HC Verma pending? Please text on the message board if you have any questions from HC Verma which are pending in work by energy. Okay, Kunj, we will start with that. Okay, so we are going to do question 61 and 62 from HC Verma. So go through question 61 from HC Verma. We will discuss shortly. Okay, Ayush, we'll discuss 62 also. Okay, so I'm putting up question 61 on the board. Let's begin with the discussion of this. Okay, so let's understand question 61. So what's happening here is that we have a smooth hemispherical surface. And from the top of the surface, we are imparting an impulse on a particle so that it sets off with a velocity v0. Okay, so this is a smooth hemispherical surface. Of radius r. Or it could be a smooth spherical surface also, it doesn't really matter. Now, from the top, a particle of mass m is given a horizontal impulse so that it develops a velocity of v dot, let's say, or v or whatever. So we have to find the normal reaction just after the impulse is applied. So we have to find the normal reaction acting on the particle just at this instant when this impulse is applied. So if the particle is experiencing some normal reaction, that means it is in contact with the surface. Okay, and if it's in contact with the surface, that means it's in circular motion. The path of the particle is circular. So the centripetal acceleration on it must be equal to mv naught square by r. So mg minus normal reaction must be equal to mass into centripetal acceleration. So normal reaction should be equal to mg minus mv naught square by r. So as you can see from this equation, we can also see that for n to be greater than 0, that is the body or the particle to be in contact with the surface, okay, n greater than 0, that means the particle to be in contact with the surface, okay, mg should be greater than mv naught square by r, or v naught should be less than root gr. So in other words, if v naught is greater than equal to root gr, then the particle loses contact with the surface at the top. So that answers your part B also. Okay. So this is clear so far now. Kunj, this is clear na so far. Okay. Now see, in the next thing what we are doing is, if the speed at the top, if v naught is equal to half the minimum value in part B, that is v naught is half of root gr. Okay, so that's the C part. If the speed is half of this minimum value, then we have to find the angle made by the radius through the particle with the vertical when it leaves contact. So we have to find the angular displacement at the point when it leaves contact. Okay. So this is where our application of work energy theorem will come in. It's for the third part only that the application of work energy theorem will come in. The rest was just dynamics as you saw above. Okay. Okay, Dvisha, I'll come to those questions also. So let's understand this part. So now we are assuming that we are giving it a speed of half of root gr. Okay, so we will solve the problem for that. So let's magnify this a little. So if we are giving a speed of half of root gr, okay, then definitely we can see that at this point of time, it is going to maintain a normal reaction. So in fact, we can see that this normal reaction initially will be mg minus this. So it will in fact become mg minus mg by 4, or it will in fact be 3/4 of mg. This will be the initial normal reaction. Okay, at t equal to 0 when we've just projected the particle. Okay. Now, like the question says that after some time, suppose it has slid down the inclined plane and reached somewhere here, so that its angular displacement is theta. The angle is making with the vertical for the position vector, that is theta now. So at this point of time, if it is losing contact, we have to understand what is the condition for that. So यहाँ पे its speed has become v in the tangential direction. And at this point of time, we are saying that the normal reaction should have become 0. So there's only one force acting on it, that is mg. So the condition for us is that at this time t, if normal reaction has become 0, it means that mg cos theta itself is equal to mv squared by r. So this equation is clear, Nakunj? This is the condition for normal reaction to be 0. And the other thing, okay, so that is the condition. Now the other thing is we can relate V with V naught by using work energy. So conservation of mechanical energy from t equal to 0 to t equal to t. So basically from this point to this point, if we are applying conservation of mechanical energy, we can see that it's coming down from here to here through a height of h. Okay, so our work energy theorem will become half mv square minus v naught square, okay, change in kinetic energy, minus change in potential energy, should be equal to 0. Now from the diagram you can see that between these 2 points, this is our h, this point is O, this is r, this is theta. Also this whole thing is r, no? Whereas in this triangle you can see this thing is r cos theta. So h is equal to r minus r cos theta. Yes, okay. So we have so from this we have v square is equal to v naught square plus 2gr into 1 minus cos theta. And remember v naught was half of root gr. So we have v square is half root gr square. Okay. So now from equation 1, v square is equal to gr cos theta. Okay. So substitute that here. Sorry, this should be plus. Plus. Because v square is v naught square plus 2gr 1 minus cos theta. So this will become our final answer. The answer given at the back is different, so let's just check our value once more. Oh, sorry, by mistake in the calculation. When we cancel the GR on this side, we will have cos theta. No? This equation is not 1 on this side, it's equal to cos theta on this side. So we have okay. So we have 9 by 4 is equal to 3 cos theta. So we have theta is equal to cos inverse of 3 by 4, or cos inverse 0.75, which if you calculate as an angle, it's, it's about 41.4 degrees. But the answer given at the back is in cos inverse form only. So this is the answer. Okay. So I'll just minimize this for a moment, and this is an important type of question, though it's in vertical circular motion. So you have done it as part of your circular motion also, but there's the application of work energy, as you can see. Okay. So this is the C part of question 61. Okay, from HC Verma. Yeah, Kunj, that's correct. Okay. Now we'll do 62 next, right? Next, we are going to do question 62. So just go through it. We'll discuss. Okay, let's move on to question number 62 next. So there we have a situation like this. We have a spherical surface with an inclined plane coming out of it like this, such that this angle is theta. So it's a smooth surface which consists of an inclined plane followed by a smooth spherical surface like this. So this total length is L. And the radius of this surface, this spherical surface, is R. So one interesting thing you'll see here is that if we draw the tangent here, this angle should be actually 90 degrees. So we'll draw this more carefully. So the other thing is that if this angle is theta, that is the angle that the inclined plane is making with the horizontal, then this angle here will be again theta. It is easy to understand because if we just drop a vertical from this point, you can see that this angle is theta, therefore that angle is theta. Okay. So anyway, now what is happening is we are taking a small block, which we can treat more or less like a particle. Okay. So a particle of mass m is projected from the bottom of the inclined plane. So from here we are projecting it with some initial speed, let's say v naught. So it goes sliding up the inclined plane like this. So we have to find the minimum projection speed at the bottom for which it reaches the top. So for it to reach here at the top, say this point is B. So first part is we have to find minimum projection speed at A, so that the particle reaches the top point B. Okay, so for that we have to understand that at B, the kinetic energy should be greater than equal to 0. Okay, so for V naught to be minimum, kinetic energy at B should be equal to 0. So A to B, change in kinetic energy plus change in gravitational potential energy should be 0. So minus half mv naught square plus mgh should be 0. Now what is h over here? H is this height difference from B to A, this whole height difference. This is h. ये पूरा height difference. So this whole height difference, you can see, you can break it up into two parts. This much is L sine theta, and then this much above over here is how much? R into 1 minus cos theta. It's clear, na Kunj? Again, that right angle triangle at this. So this H is equal to L sine theta plus R into 1 minus cos theta. So we substitute that here. So V naught should be equal to 2gh square root, or square root of 2g into L sine theta plus R into 1 minus cos theta. This will be that minimum speed. So that's your answer to part 1, part E. Okay, so hope this is clear, Kunj. Okay, good. And Ayush, hope this is clear for you also. Okay. Now in the second part, see what we have to do. Assuming the projection speed is 2v naught and the block does not lose contact with the track before reaching top, find the force acting on it when it reaches the top. So by force, we mean normal reaction force. Now C part, assuming that the projection speed is only slightly greater than v naught, where will the block lose contact with the track? Okay, so let's understand the B and C part next. Okay, so let's come to the B part. So in this, what is happening is assuming that the projection speed is 2v naught and the block does not lose contact with the track before reaching the top. So we are giving a speed of 2v naught here, which is equal to 2 times square root of 2g L sine theta plus R into 1 minus cos theta. So we are giving that speed here. Then when it reaches the top point here, The speed is, let us say, v prime. So the forces acting on it will be normal reaction in mg. So first of all, how we'll find v prime? This should be equal to, where h was what we had calculated earlier, this whole height from here to here. So h is this quantity, L sine theta plus R into 1 minus cos theta. So at the top, the speed v prime will become square root of v square minus 2gh. Now v is this, so we'll just substitute. Twice of this. So when you square this term, it will become 8gl, 2 root 2's whole square, into L sine theta minus R into 1 minus cos theta. So that's your v square. Okay. Minus 2gh, so that is minus 2gl. This term, okay. Here also there's no L outside, it's just 8g. So 8 minus 2, that becomes 6g. So v prime, you can see, becomes square root of 6g into L sine theta minus R into 1 minus cos theta. Becomes like this, okay. So once we've got the v prime for this given value of v, next thing what we'll do is we'll find the normal reaction from the free body diagram. Therefore, mg minus n is equal to mv prime square by r. So normal reaction is mg minus mv prime square by r. So if you do that calculation, with mg common, you can see you'll get 1 minus 6l by r sine theta plus 6 minus 6 cos theta, something like this. So you'll get mg into 7 minus 6l by r sine theta minus 6 cos theta, something like this. You'll get as the contact force. I think the question is asked for the net force, is it? Or has it asked for normal reaction? So I think it's asked for net force, that is mv prime square by this thing only. So what the question is asking is not normal reaction, it's asking for the net force. So the net force acting on it is mg minus n, which is mv prime square by r. So it's just this much only. 6 mg into L by R sine theta minus 1 minus cos theta. Sorry, plus 1 minus cos theta. Okay. So this is the net force. whereas this is a normal reaction. So what the question is asked is this, the net force. Okay, so again, hope this is clear. Kunj and Ayush. Okay, now let's come to the third part. The third part is a bit tricky. Assuming that the projection speed at the bottom is slightly greater than V naught, that means is almost equal to V naught. Okay, we'll have to assume that it's equal to V naught, which was that quantity, root 2G into L sine theta plus R into 1 minus cos theta, this term. Okay. So assuming it's slightly greater than this, okay, then we have to find the position at which the normal reaction becomes zero. So again, this is that type of question that we have to assume some position in between, okay, and then find out the condition for normal reaction to become zero, and then again find out the work energy relation. Okay, so we can do this question in a slightly easier way actually. Instead of solving the work energy relation that way now, if we assume that because it's slightly greater than V naught, the particle reaches the top point of the circular part of the track, okay, with a speed, let's say u, which will be slightly greater than zero, because the speed that we are giving here is slightly greater than V naught. So this u is almost tending to zero at the top. Okay. So from here, if it goes to a position like this, to some angle, let's say phi or something, where it loses contact. Okay. So normal reaction here becomes zero. And again, you can see the condition for that will be that mg cos phi should be equal to mv square by r. Okay. And from work energy, half mv square should be equal to mgr 1 minus cos phi. Okay. So solving these two equations, you will see that okay, which from the first equation is this. So we will get 2 into 1 minus cos phi is equal to cos phi, or cos phi is equal to 2 by 3. So therefore, it will lose contact at phi equal to cos inverse 2 by 3 is the angular position at which the contact is lost. Okay, so this is the solution of the 62nd question, the C part of the 62nd question. So hope this is clear, Kunjan, Ayush. Okay, so now next, if you're finished with HC Verma questions, yeah, we will come to the new chapter also. But if there are any doubts in the module, let me know that also. We'll cover that first. Okay, we will pick up the next chapter now. Which will be heat and thermodynamics. Okay, students, let's resume. Yeah, unfortunately, some technical problem with my camera. Anyway, we will start heat and thermodynamics. So this is the next section of physics for us. All right, anyhow, so let's begin the next section, heat and thermodynamics. So this section, we will start with a chapter called heat and temperature, okay, where we will begin by understanding temperature scales and then thermal expansion of materials, and then the principle of thermometry. In the next chapter, we will see is called calorimetry, where we will understand the concept of specific heat capacity and latent heat, that is state change in matter. And then the next chapter we will see is kinetic theory of gases, followed by first law of thermodynamics and its applications. And followed by the last section, which will be heat transfer, where we'll understand the concepts of conduction, convection, and radiation. Okay. So collectively, this entire portion has about 15% weightage in JEE, mains or advanced. Okay. And it's comparatively easier than mechanics. So we should be able to find it easier to solve. Okay. So comparatively, it is more scoring compared to chapters like friction and Newton's laws of motion and work by energy. Somewhat easier to follow also. So this is all, this section is in your module 3 in physics. So in case you don't have the module 3, please let me know, or please collect it from your respective centers, or you can drop me a message and I'll send you the PDF of module 3. The PDF is also available, but it's better that you have the physical copy with you. Okay. So anyhow, let's begin. So we'll start with the first chapter of heat and thermodynamics, which is heat and temperature. Yeah, both. In JEE Mains as well as Advanced, the weightage is approximately 15%. So anyway, the first chapter, heat and temperature, let's begin by understanding different temperature scales. So the temperature scales are The SI unit of temperature, which is kelvins, or also called the absolute scale. So in this, the melting point of ice is 273 Kelvin, and the boiling point of water is equal to 373 Kelvin. Okay. Yes, and there is a particular significance to 0 Kelvin. It is called absolute zero, because it is the temperature at which molecular activity, that is motion of molecules in the form of translation, rotation, or vibration. So this type of molecular activity ceases altogether. So it is a what we call a theoretical temperature. This is hypothetical. Okay, it is not achievable in practical physics. Yes, minus 273 degrees C or 0 Kelvin, they are one and the same thing. That's correct. So that is the hypothetical temperature at which molecular activity ceases to exist. So that's why it is called the absolute zero. Okay, so it's a significant quantity in thermodynamics, but at the same time, it is not achievable in practical physics or in laboratory physics. As you might be knowing that superconductivity is a property of matter that exists at extremely low temperatures. Yeah, it's not possible because see what is happening is that to make the molecules cease of any type of motion, all molecular motion has to be absorbed through collisions, and no collision can be such that the final motion of a molecule will completely be absorbed. It's simply not possible. Some fraction of molecular activity will always remain even after absorbing it through collisions. Okay. So that is the idea. So that is the significance of absolute scale. Okay. Now the second temperature scale is the most common one, which is the centigrade scale or Celsius scale. This is what we refer to in degrees C. Yeah, Rupesh, what is your question, madam? If there is motion between molecules, then definitely the temperature will be greater than 0 Kelvin. So in centigrade scale, melting point of ice is 0 degrees C, and boiling point of water is 100 degrees C. Yeah, Ayush, this is the definition of absolute zero I've written down here, so you can just note this down. This is what I was explaining, that absolute zero is 0 Kelvin, or that's the same thing as minus 273 degrees C. It is the temperature at which the molecular activity ceases. Ceases means does not happen anymore. Ceases to exist. Okay, Aditi. Ceases means ceases to exist. So no molecular activity. That's why it's a hypothetical temperature. It's a temperature that's only theoretically possible. In practical physics, we cannot achieve 0 Kelvin. Okay. Now, the conversion between degrees C and Kelvin is that x degrees C is equal to x plus 273 in kelvins, or y kelvins is equal to y minus 273 degrees C. So, for example, 27 degrees is equivalent to 300 Kelvin, and 400 Kelvin is equivalent to 127 degrees C. So this is the simple conversion from Kelvin scale to degrees C and vice versa. Okay, now the third temperature scale is the Fahrenheit scale, which is referred to as the degree F. So in this, the melting point of ice is 32 degrees Fahrenheit, and the boiling point of water is how much? Anybody knows? Yes, correct. 212 degrees Fahrenheit. Okay. So you can see that conversion from Fahrenheit to degree C, x degrees Fahrenheit is equal to x minus 32 multiplied with 5/9 in degrees C. Okay. And conversion from degree C to Fahrenheit, y degrees C is equal to 32 plus y into 9/5 in degrees Fahrenheit. So the reason for this is pretty simple to understand, that an interval of temperature equal to the temperature of boiling point of water minus melting point of ice. So that delta T is 180 in Fahrenheit, and that's equal to 100 in Celsius. So an interval of delta T equal to 1 degree C is equal to 180 by 100, or that is the same thing as 9/5 degrees Fahrenheit. And an interval of 1 degree Fahrenheit is equivalent to 5/9 in degrees C. Yes, very interesting, sir. That's correct. There's an additional point that a reading at minus 40 degrees Fahrenheit is equivalent to a reading at minus 40 in degrees C. That is where the two scales coincide. So if you put x as minus 40 here, you will get this as minus 40 only. If you put y as minus 40 here, you will get this as minus 40 only. So that's very interesting observation, Ruksar. That's correct. Anyhow, so let's look at a quick question before we move on. So this is very easy stuff you've done in 9th, 10th, I'm sure. But let's look at a quick example. Convert 40 degrees C to degrees Fahrenheit and Kelvin, and convert 77 degrees Fahrenheit to degrees C and Kelvin. Just work this out quickly, people. Okay, people, I'm checking the answers. Yeah, very good. Correct, Aditi, Ruksar, Hitanshu. Okay. Just putting up the answers for everybody. So the first one, 40 degrees C will be equal to 32 plus 40 into 9 by 5 in Fahrenheit. So it will be 32 plus it will be 104 degrees Fahrenheit. Correct. And also 273 plus 40. So that is 313 Kelvin. Now, for some historical reasons, Kelvin is never written with a degree. Okay, it's an interesting reason. I find that out later why that is the case. Okay. Yes, very good. That's correct for the second part also. Rupesh, your answer is correct. So 77 degrees Fahrenheit will be equal to 77 minus 32 into 5 by 9. So that will be 25 degrees C. So 77 degrees Fahrenheit is 25 degrees C. So that will also become equal to 25 plus 273 or 298 Kelvin. Okay. So I mean, this is just too easy. Just for reference, I'm giving you one simple question like this. It's not that you will get direct question like this in JEE. It's just that the data in one question might be given in one scale and you have to convert. So part of that question, you have to know the conversion. Okay. Now let's come to our first important section, which is thermal expansion. So all materials, regardless of their state of matter, solids, liquids, gases, everything, solids, liquids, and gases tend to expand. That means their physical dimensions tend to increase. Okay. On raising their temperature. Okay. And conversely, they tend to contract on decreasing the temperature. So this is an experimental observation, you can say. Okay. Now what we mean by physical dimensions is that, for example, if we have a solid block, so it has dimensions, length, width, and height. Okay. So on raising the temperature or on increasing the temperature, okay, length, width, height, all of these will increase. Okay. Surface area, will increase. Volume will increase. Okay. So all dimensions, this is what we mean by the physical dimensions or the physical size. Increases, but such that the shape remains same. And by shape we mean even the proportions remain the same. So if you increase the temperature of a cube, it will remain a cube. It will not become a cuboid, or it will not become rectangular from square. A square plate's temperature increased uniformly will not change its shape into a rectangular plate or something. The sides will increase in proportion such that its shape will remain square. A spherical body will remain a spherical body, but of larger size, larger volume, larger radius. It will not bend into an ellipsoidal shape or some other shape. Yeah, so we are coming to that, why that happens. I'll explain that. That happens because of the principle of linear expansion, basically. Now, you can also say at one level that it's experimentally observed, that is what happens. But the mathematical reason for it is because of the principle of linear expansion. That is, that the length dimension of any body changes in such a way that the fractional changes in length is directly proportional to the change in temperature. But anyhow, first just make sure you noted down this part and understood the concepts up to this point. The next thing we'll see is the law of linear expansion. Yes, and that's what we mean by proportion. We mean the ratio of the measurements. So I'll explain with an example what we mean by this. So what is happening is that suppose, for example, we have a cuboid like this, whose dimensions at some temperature, at temperature T1, the dimensions are L1, B1, and H1. Okay. At a new temperature, T2 equal to T1 plus delta T. Your new length will become L1 plus delta L. Your new width will become B1 plus delta B. Your new height will become, sorry. So this whole body would have expanded from its original dimensions like this. Okay. But such that L1 is to B1 is to H1 will be equal to L2 is to B2 is to H2. This is what we mean by saying that the shape remains same, or the body expands proportionately with rise in temperature. So yes, the size does increase, but the proportions remain the same. So this is something you can say is observed. It's part of the properties of matter which is observed, that thermal expansion happens in this way. Yes, yes, this is from everyday life only, beta. This observation is from, but you don't always notice it in your everyday life because the increase is very, by a very small fraction. But in certain situations, even in everyday life, it becomes significant. Yes, this happens at the practical level. And because it happens in everyday life, so in engineering, we have to account for thermal expansion. Like you might have heard of a device called a bimetallic strip that is used as a fire sensing alarm. So that works on the principle of thermal expansion. Yes, it's correct. We have to take it into account in civil construction of highways or railway tracks. Wherever railway tracks are joined together, there's always a very small amount of gap left. That is so that the railway tracks will not bend due to stress on expansion on summer days, and they will fill that gap. Or if you have a metallic frame on which a glass window pane has been put, there will always be a bit of glass, a bit of gap between the metallic frame and the glass, and some rubber sealant will be put in that gap, because the glass expands at a faster rate compared to how the metal expands. So if you don't leave a gap and put sealant over there, then the glass will shatter on thermal expansion. So these are all very much everyday issues that have to be dealt with at engineering and technology level. Yes, glass also expands. Then in structural and civil engineering, where you have steel structures or you have cable bridges, etc., where the load bearing is done by steel cables or by steel structures, thermal expansion plays an important role and has to be accounted for in the load bearing part of it also. Yeah, so melting of glass, that is the other thing. So matter not only expands, but on heating, matter can also change state from one state like solid to liquid, and then from liquid to gas. So melting of glass at very high temperatures, an example of state change from solid to liquid. So that's also correct, Beshi. But currently we're discussing that within the same state, thermal expansion takes place before you reach the melting point. Understanding, even if you have a metallic object and you heat it a lot, once it reaches the melting point, instead of expanding further, it will melt into liquid metal. Mercury is the only metal which at room temperature exists as in liquid form. Other metals all exist in solid form in room temperature. They have to be raised to a very high temperature to melt them. But till we reach the melting point, within the solid state itself, we observe the phenomena of thermal expansion. So next, let's come to the first mathematical formula involved, which is the law of thermal expansion. And in this set of laws, the first part will be linear expansion. So the principle or the law of linear expansion is that any linear dimension L, okay, increases with a change in temperature such that the fractional change in length is proportionate to the change in temperature. And the constant of proportionality is given a special name, and it is called the coefficient of linear expansion. So alpha over here is called the coefficient of linear expansion. Okay, so now this quantity alpha, which is called the coefficient of linear expansion, this is what we call a material property. Alpha is a material property of the given body. Okay. So it actually, it's a constant that depends on the material of the body. Okay. So for example, two blocks of copper, okay, of different dimensions or size will have the same value of alpha. Okay, because they are both made of same material, copper. Okay. Whereas two blocks of identical size or identical dimensions, but made of, let's say, copper and aluminium, they will have different alphas. Because they are made of different materials, okay, of alpha. So that's one thing. Now the other thing to note in this is that delta L by L, it is a fractional change. It's a fractional change in length. So it is a dimensionless quantity. Okay. Or unitless quantity. So that's why alpha is expressed in per degree C or per Kelvin. That is, we can express it like this: per degree C or per Kelvin. Okay. And for metals, the value of alpha has the order of magnitude of 10 raised by minus 6 per degree C. So most metals typically have a value of coefficient of linear expansion whose order of magnitude is 10 raised by minus 6 per degree C. No, so the thing is, alpha is experimentally determined for all metals. Okay, just like we determine properties like elasticity, density, uh, this thing, malleability, etc. So like that, coefficient of thermal expansion also for all materials required for engineering purposes or structural purposes, it is experimentally determined. So there's no theoretical way to calculate alpha. Okay, so that point also you can note down separately, that alpha for all materials is experimentally determined. So that is why in engineering manuals you will find, yeah, ductility also, that's correct. Ductility, then for metals, the electrical conductivity becomes important. Then later we'll see in heat transfer, there's another property called thermal conductivity. So all these type of physical properties or mechanical properties or thermodynamic properties, whatever be the case, they all have to be determined experimentally, because they are taken into account when we design any structure or machine or uh, any device using the different type of metals and different type of materials. So it's very much part of engineering to be able to understand the significance and properties of different materials and material properties. And in engineering manuals, all these things are listed in tables. So the values that are listed in engineering manuals, they are actually determined by competent authorities which do the experimental analysis. Okay, so they are experimentally determined. So for example, even on the internet, if you type that what is alpha for steel or what is coefficient of thermal expansion for aluminum or something, you will see that you will get a particular value from various different sources. So that value has actually come from some experimental analysis, and it is published in journals or in in engineering manuals, as I told you. So anyway, at our level, we don't need to worry about that. The value of alpha for us will be given in a question when we're doing calculation. So let's look at a typical example question. Yeah, it is different for all metals. That's correct. No two metals will have the same value of alpha because no two metals have exactly the same, this thing, material structure. Na? The way the atoms are arranged in the crystal lattice of the metal and all that, they're different. The type of interatomic bonds within the structure of the metal, they're different. So the value of alpha will accordingly be different for different metals. So every element in the periodic table, it has a unique chemistry, and therefore all its physical properties are unique. So whether we are talking about coefficient of expansion or density or malleability or ductility or electrical resistance or resistivity, that is, or any such physical property, they will have different values for all different elements and compounds for that matter. So anyway, let's look at an example. So suppose, so let's start with something very simple. So we have a metallic rod, which is so this is a metallic rod. Now this has a length of, let's say, 50.000. So we have determined it up to millimeter accuracy at a temperature of 27 degrees C. This is roughly room temperature, 27 degrees C. If alpha for that metal is equal to, let's say, 0.4 into 10 raised power minus 6 per degree C, then find the percentage change in its length, okay, and its length itself, that is the new length, at a temperature of 227 degrees C and at a temperature of minus 73 degrees. Yes, alpha will always be given in the question, or the data given in the question will be such that we can calculate alpha from that. So we'll have two kinds of situations in questions. Either we have to use the value of alpha that is given already, or some information will be given from which we can back calculate and find the value of alpha. Okay. So typically the calculation is very easy in this chapter. We have to just use this relation which you talked about earlier, that fractional change in length is equal to coefficient of linear expansion into change in temperature. This is what we have to use. Okay. So for the first part, so delta L, now we can also write it like this, that this is L2 minus L1 upon L1 is equal to alpha into T2 minus T1. This we can write like this. If L is equal to L1 at T equal to T1 and L is equal to L2 at a temperature of T2, then the fractional change in length for changing the temperature from T1 to T2 is change in length, that is L2 minus L1 upon original length, which is L1, and that is equal to alpha delta T, which is alpha into the change in temperature. So we can use this also. Okay? So L naught is equal to 50.000 meters at T naught is equal to 27 degrees C. Now let's say L we have to find out at a new temperature of 227 degrees C. Okay. So delta L by L is equal to alpha delta T. We can interpret this like this: L minus L naught upon L naught is equal to alpha into T minus T naught. So the fractional change in length is equal to alpha, which is 0.4 into 10 raised power minus 6 into the temperature change, which is 227 minus 27. So first we will calculate the fractional change because we want the percentage change, and then later from that we will find the actual length. Okay. So we will come back to this calculation, but first we will find this. So delta L by L is how much now? 4 into 2 into 10 raised power. Uh, this is 200. No? So 10 raised power minus 5. So that is 8 into 10 raised power minus 5. Sorry, into 10 raised power minus 3. Minus 3. This was correct only. Okay. So the percentage change in length will be delta L by L converted into a percentage by multiplying by 100. Okay. So that will be so 0.08% change. So that's the first thing. Okay. And then we can substitute that here and we can understand that therefore L will be L naught plus L naught into alpha delta T, or it is L naught plus delta L. So the new length will become 50 plus this value, 8 into 10 raised power minus 5 times 50. So as you can see that it will expand by 4 millimeters. Okay. So the delta L, this is 0.08%. So that means the expansion is 0.08% of 50 meters, which is 4 millimeters. So the length expands by as less as 4 millimeters. Okay. So So this is the new length at the temperature of 227 degrees C. This is the new length, and it has expanded by 4 millimeters for this temperature rise. Okay, so that is why thermal expansion is not so noticeable in everyday life, other than certain situations, because you can imagine a 50-meter long rod is a very, very long rod. Now 50 meters is roughly 150 feet. So it's a very, very long rod. You can think of it like one of the rail tracks, that kind of. So that one will expand by a very minuscule amount, less than half a centimeter. 4 millimeters is less than half a centimeter when expanded through 200 degrees C. It's a huge amount of temperature rise. So it's hardly anything noticeable. So going from a winter day to a summer day, the temperature change is going to be hardly, something like 30 to 40 degrees C even. So it's not going to be something very noticeable. However, it makes a difference in precision instruments, and we'll be talking about that later in the next lecture. For example, the pendulum of a clock, of a mechanical clock, its precision depends on its length. So the length changes by even a small percentage. The clock will start to lose or gain time. So over a period of one day or several cycles, it will lose a significant amount of time. Okay, so anyhow, that's it for today's session, people. Wish you all the best. Yes, I will send you the notes and the recording of it soon.